Okay, everyone, thank you for your patience. My name is MJ Gautrau. I'm the communications lead at the Advanced Structures and Composites Center, and I'm filling in this week for Erin Shank. Good afternoon and welcome to the Transportation Infrastructure and Durability Center April webinar on process glass aggregate and Scarborough. Switch slides for you rather. There we are. The Transportation Infrastructure Durability Center is the 2018 US DOT Region 1 University Transportation Center located at the University of Maine's Advanced Structures and Composites Center. TIDC's focus is on extending the life and improving the durability of transportation assets through 4 research thrusts seen here: advanced structural performance assets, development and implementation of novel materials, advanced structural systems and applications, and enhanced performance through innovation and safety, resilience, and connectivity. TIDC has 6 member universities within the New England region: the University of Maine, the University of Connecticut, the University of Vermont, the University of Western New England, University of Massachusetts Lowell, and the University of Rhode Island. Today's webinar will consist of a brief introduction to PGA, followed by a 40-minute presentation and Q&A session to wrap up today's activities. During the presentation, we are going to be using the Zoom Q&A feature. See that right here, to answer questions, and we'll go down the list of those questions during that Q&A session. If we pardon me, so excited about this webinar. I'm speaking so quickly today, aren't I? If we don't get through all of the questions during our scheduled time together, there will be a link at the end of the webinar to submit any further questions, and we can email you a follow-up. Our first presenter today is going to be Dr. Mandar Dewoolkar of the University of Vermont. Professor Dewoolkar has almost 20 years of experience as a researcher, consultant, and educator. He specializes in geotechnical and geoenvironmental engineering. His research involves applying physical and numerical modeling and field laboratory testing techniques to study effects of environmental loadings, hazards, and extreme events on natural and human-made materials and structures. His research is interdisciplinary, and he routinely collaborates with structural, environmental, transportation, mechanical, aerospace, and electrical engineers, hydrologists, geographers, geologists, historical preservationists, statisticians, and education and social scientists. He is UVM's Sustainability Fellow, Service Learning Fellow, and Fellow of Gund Institute for the Environment. Professor Dewoolkar's research has been funded by a variety of agencies, including the National Science Foundation, Defense Threat Reduction Agency, Los Alamos National Laboratory, National Park Service, the U.S. Department of Transportation, National Center for Preservation Technology and Training, Vermont Space Grant Consortium, and the Vermont Agency of Transportation and Agency of Natural Resources. Since 2003, Professor Dewoolkar has been working with 3 postdocs, 25 graduates, and over 50 undergraduate students. Our second presenter today will be Dr. Matthew Scarborough, also at the University of Vermont. Dr. Scarborough's research focuses on the application of microbiomes, aka microbial communities, to protect the natural environment and public health. His current focus include 1, management of organic waters with the goal of harnessing reactor microbiomes to convert renewable feedstocks into valuable products, and 2, reducing greenhouse gas emissions from landfills with soil microbiomes. Dr. Scarborough's work encapsulates many scales, from studying the function of individualized enzymes to implementing full-scale microbiome-based conversion platforms. Dr. Scarborough earned his PhD from the University of Wisconsin-Madison, where he worked as part of the Great Lakes Bioenergy Research Center. He previously worked for a large environmental consulting company as a wastewater engineer and is a licensed professional engineer in Vermont. In addition to conducting environmental engineering research, Dr. Scarborough uses teaching as research framework to assess teaching practices and develop a learner-centered courses. And then they are joined today by Nick Vandenberg of Vermont Agency of Transportation. Nick is a materials manager at the Vermont Agency of Transportation and a valued collaborator of TIDC Project 2.12, evaluation of processed glass aggregate for the utilization in transportation projects as a sand borough. So without further ado, the floor is yours, Nick.
Thank you, MJ. I think Dr. Mandar, you're going to start, and then
Yes,
I'll jump in.
I will start, and Nick is going to come in after about a couple of slides. So thank you, MJ, and great job filling in for Aaron. We greatly appreciate the opportunity to present today. The topic from the that was advertised, we elaborated upon a little bit here on the slide, which says processed glass aggregate or glass cullet. So our focus has been on quantifying the deleterious materials content, what are the allowable limits, and the economic analysis to see the viability of using glass cullet in construction, particularly in Vermont as a case study. You will see two additional photographs here. Those are our grad students who worked on the project and did all the tedious experimental work and analysis, Neha and Fiona. And we wouldn't be able to present this work today without their hard work. As we move forward, you will notice there is a number in the upper right-hand corner of the slides, and those are the slide numbers. If you have any questions about a particular slide, you might be able to refer to those numbers. You see a beautiful picture of our campus, and as a dean of our college, if this actually moves forward, okay. I thought I'll plug in for our university. It's a beautiful campus. University of Vermont is located in Burlington, which is on Lake Champlain. And to the left, we see the photograph of Burlington from the lake. And next to it, you see New York State, if you are looking on the other side of the lake. And Vermont has a lot to offer, including the city of Burlington. So if you are considering of going to grad school, or you know someone who is considering college, please consider coming to University of Vermont. With that, I'm going to hand it over to Nick, who is going to orient us on why this project, how it took shape.
Thank you, Mandar.
I'll just read all of those things. There you go.
Thank you. Yeah, so sort of where this started for the Agency of Transportation. We were approached by one of our glass recyclers when their outlet for processed glass cullet stopped accepting the material. So this glass cullet in particular was appealing from an engineering perspective initially, just because it's processed to a particle size that's similar to that of a coarse sand, as opposed to other glass cullet that might typically be like a 3/8 minus or a 1-inch minus. This material is processed to a very small particle size. So this then was brought to our recycled materials working group, which is a collaboration between the Vermont Agency of Transportation, the Vermont Agency of Natural Resources, as well as our industry partners and recyclers. So within that group, we work together to find beneficial reuse for recycled materials and manufacturing byproducts. So a little history, the Vermont Agency of Transportation standard specifications for construction has allowed for the use of up to 10% PGA blended into sub-base material since at least as far back as our 1995 edition. But to our knowledge, no contractors have really been using that option. We also reviewed the standard specification published by AASHTO, designated M318, which is titled the Glass Cullet Use for Soil Aggregate Base Course. And that standard provides guidance for using up to 20% PGA blends for road-based materials. So that led to one of the research goals, which was to determine the engineering suitability of using something greater than a 20% blend. And also with this material in particular, given the similarity to Scarborough We also wanted to determine engineering suitability of replacing Scarborough with this material up to 100% replacement, as that could provide a very economical use case for contractors if there was no blending required, if they could just use it straight from the materials recovery facility. And of course, one of the risks when using PGA is the presence of deleterious content, such as paper, plastic, metals, and organic materials. So both our existing specifications and the aforementioned AASHTO M318, they both provide limits for deleterious content in PGA. And so in the interest of simplifying our specification requirements concerning deleterious content, we also wanted to learn through this project what the engineering limits are for the typical categories of deleterious material. And this focus on deleterious material brought us to another major objective of the project, which was to find a more practical way of determining the deleterious content in the PGA. So AASHTO M318 provides a method for determining deleterious material content, but it requires hand sorting of particles to manually separate glass, paper, other, and soils. But again, this material being such small particle size, it really wasn't a practical method. And so hand sorting such small particle size likely would be very tedious and provide questionable results. But I'll say overall for me, one of the important things from the agency perspective was that this project was going to answer our specific engineering questions. And we knew before the project even started exactly which parts of our specifications we would update based on the outcome of the project. Thank you, Mandar.
Thanks, Nick. So with that in background, this study is funded by Transportation Infrastructure Durability Center and was also supported by CSWD, which is one of the local recycling facilities, Agency of Transportation, Agency of Natural Resources, and so on. So our goal was to develop reliable and operationally simple that one can easily determine the deleterious material content in glass collect, all crushed recycled glass, which we'll call PGA throughout the presentation. And once we started working on the project, there was quite a bit of interest in figuring out how much plastic was there in PGA specifically. So we focused on coming up with those methods that were simple. And then the literature, if one looks in the literature, typically you find evidence that the blends or the actual PGAs acquired from recycling facilities had acceptable geotechnical properties, but there was no systematic study that we found that actually studied effects of a particular percentage of deleterious material and what would be allowable deleterious material content. So we worked on that. And for Vermont, we wanted to study the economic assessment of using crushed glass instead of Scarborough, the material that's used as a free draining material, which is typically granular material with less than 5% fines. Finally, hopefully this project will lead to more widespread use of PGA in Vermont and beyond. So the first question is how to reliably determine deleterious materials contained in PGA and also plastic in PGA. And our focus was reliable and operationally simple methods. And for that, we use PGA acquired from recycling facilities, as well as we made our own PGA in the lab where we knew exactly how much deleterious material was in it. As Nick mentioned, the AASHTO standard M318 has a method which basically relies on visual observation. And the deleterious materials usually are plastic, metals, glass, food waste, plastic, paper, and ceramics are usually, China is usually considered separately. And what we realized is that it is very difficult to figure out or visually separate, particularly in finer material we see on the left, which is more sand-like. Here are 3 different materials that we obtained from Vermont recycling facility, New Hampshire, and Massachusetts. And you can see a US penny added to the picture to get a idea of the size. And particularly the one on the left and one on the right, it's difficult to separate visually all the deleterious materials and ceramics to figure out what is the deleterious material content in a given PGA that one acquires. So our materials that we studied included these three materials from 3 different states. And on the right, you see pictures of different things that you find in a PGA that is referred to as deleterious material content. But one problem with the real materials is that you don't know exactly how much deleterious material content is in it. So for that, we acquired this machine, and we acquired clean glass, and we prepared our own PGA, which we refer to as LMPGA. LM stands for lab manufactured. And the previous one we called RFPGA, where RF stands for recycling facility PGA. So here are the grain size distributions. The one to the far right is the PGA from Massachusetts. Then we see the one from New Hampshire. The one to the right is from New Hampshire, then from Massachusetts. Then we acquired 3 different samples from Vermont, from summer, fall, and winter, to see if there was any seasonal variability. And all the way to the left, which is slightly smaller grain, is the one that we prepared in the lab. And then we added different types of deleterious materials in it, office paper, newspaper. Since Vermont does single source recycling, there is usually paper that gets stuck to the glass, which makes its way into crushed glass. And of course, some plastic, some metal, and we use steel and a peanut butter to represent sticky food. And we tried a bunch of different methods. We tried chemical washing with different types of acids, boiling the material, and variety of different methods, and finally landed on 3 methods that worked well. Using a magnet to separate ferrous materials, combustion to 550 degrees centigrade, and density separation with water by just mixing the material in water and let plastic float to the top. So the acquired material, we dried to 110 degrees, and we passed it through this universal separator 3 times. And then we acquired 6 samples of 1200 grams each in order to run tests on them. So the first protocol we developed is a combination of a magnet test and then combustion. So this 1200 grams of sample, we would spread on aluminum sheets, thin, and then take a magnet over it several times until no more material was picked up. And then that would separate all the ferrous materials. And then the remaining we would put in the furnace, muffle furnace at 550 degrees for 50 minutes and mix it once after 25 minutes. The second protocol was taking 1500 milliliters of water and adding 1200 grams of PGA to it and shaking it really well and separating what floats, as we see here. And then it continued, this particular protocol. So here we see that on the top, the separated material that floated. And then after we dried it, Neha actually painstakingly separated all different colored plastics in different cans. And then she moved on to the material that did not float, including all the glass, dried it, and then visually separated everything that looked like plastic and ceramics from that material. And then different types of plastics and their sizes are seen here. They go from really small microplastics type size to several, almost over a centimeter size, and different colors. And then whatever she took out that looked like plastic or ceramic, we used a technique called FTIR. And each individual piece was put under this machine to figure out what type of plastic it is and if it is plastic or not. So I'll quickly go over some results. This one is on a lab created material. So we started with clean glass and added 2% deleterious material, 2 different types of plastics, 2 different types of paper, and 0.4% peanut butter. And here are typical results. So we tested 6 samples, 1200 grams each. So the pink highlight is protocol 1, which is a magnet test, and then combustion to 550 degrees. So we'll see there was no ferrous metal added, but still we picked a small percentage, 0.02% of ferrous material out of the glass, which we think are impurities in glass. And then when we put it at 550 degrees, about 1.9% of material burnt, whereas the total expected was 2%, because everything we added was supposed to be combustible. But when paper burns, it actually leaves some ash behind. So we measured about 1.9% instead of 2%, which is still pretty good result. And you will see across 6 samples, the variability was quite small. And all the way to the right with blue highlight is the density separation method, where we added the material and separated what floated. So we expected 0.8% to float, which was all plastic, and we recovered almost all of it in this case. The second material, we tested many materials. We just picked a few to share. Again, 98% clean glass and 2% deleterious material. But this time, instead of peanut butter, we had steel shavings. And we added 0.4% steel, and we recovered through magnet test a little over 0.4%. And after doing combustion test, again, the total material that we were able to determine as deleterious material content was again 1.9% as opposed to 2% that we added. And protocol 2, which is about density separation in water, once again, we recovered all the plastic that we added. So this, and one thing to notice here, that these tests were done on this material by 3 different operators, because we wanted to not only develop the test to be simple to administer, but also largely operator independent without requiring a lot of experience and skill. And in this particular case, all 3 operators got very consistent results, which was a good news. And each one of them tested 6 subsamples. Then we moved on to the materials that we acquired from the 3 different states recycling facilities. And here we see that the total deleterious material we were able to determine changed from about 0.5% to 3%. And the total material floated after doing the float test was between 0.1 to 0.8%. So recall that all testing was performed on 6 subsamples of 1200 grams each, which we felt like could be considered quite a bit of work. So we wanted to evaluate if we can reduce the number of subsamples. So we did statistical analysis on our data by picking all 6 subsamples for the analysis versus any 4 versus any 3. And we determined that even with only 3 subsamples, the error was less than 2%. So our statistical analysis showed that we could do 3 subsamples instead of 6. We don't want to recommend 1. I think 3 is a good number. Quickly going over plastic, when we did all the analysis, we are just summarizing some representative results on the 3 recycling facilities PGA. So if you look at the first rows where we have highlighted those numbers in yellow, about 0.2% of the material floated. And that included plastic, but some of it may not have been plastic. But after we went through the FTIR analysis, where we had to tediously put each and every individual particle of the material that we separated, we determined that only 0.04% of the total material was actual plastic. So if we had considered everything that floated as plastic, we would have been conservative by a factor of 388%. From New Hampshire, those two numbers were a little closer. What floated was 0.11%, and after FTIR analysis, almost 0.1% of it was plastic, and Massachusetts was slightly worse. But in general, it appears that, at least for the materials we tested, it is reasonably conservative to assume that everything was that floated was plastic. But if someone was really interested, they could do FTIR analysis to figure out what percentage of material was plastic. But it takes a lot of time. So in relation to question 1, we were able to show that the protocol 1 that we developed with magnet plus combustion test can be used routinely for routine assessments of deleterious material content in PGA. It does have limitation that it cannot capture the ceramics percentage and non-ferrous materials. However, based on our discussions with recycling facilities, the percentage of non-ferrous metals are supposed to be really small. And our lab tests or geotechnical testing that we did with up to 20% ceramics added to clean glass showed that geotechnical properties of glass don't change a whole lot with even up to 20% ceramics. So not being able to determine ceramics appears to be not a big deal. Protocol 2 works well to determine plastic, but at this point, we are not recommending it because of its time-consuming nature, unless stakeholders are specifically interested in figuring out the plastic content in the glass. And both protocols are reliable and operator independent. We were able to show that. And for protocol 1, 3 samples were sufficient. Question 2, in interest of time, I'll quickly present these. Our focus was to see if we can substitute these free draining granular films used in construction as borrow materials with glass, crushed glass. And we focused on the properties of hydraulic conductivity, compressibility, and shear strength of 3 typical sand borrow materials that Vermont uses, which are shown as solid lines in this grain size distribution curve. Then 3 recycling facility PGAs, and also clean glass that we created in our own lab. But we also added different known amounts of deleterious material, like 5% plastic, 5% paper, 5% ceramic, and 20% ceramic. Nick was interested in knowing what is the impact of each one of these materials if we were to allow 3% paper or 5% or 3% deleterious material content or 5%, what if all of it was paper? So that's why we did this study. We also have data on 3% plastic and so on. So we did a simple hydraulic conductivity test using standard constant head permeability testing. And here are the results. So the one on the left in blue are the 3 borrow soils. So borrow 1 permeability or hydraulic conductivity varied from about 0.05 centimeter per second to 0.055 centimeter per second. And we see borrow 2 and borrow 3 also. So overall, across the 3 borrow materials that we acquired, the permeability varied from about 0.001 centimeter per second to about 0.055 centimeter per second. And then the next green column is for the 3 recycling facilities PGA we had. And then the right are all the clean glass that we prepared with different types of different materials added, like paper, plastics, ceramics, and things like that. And these results show that all the materials we tested had hydraulic conductivity higher than the lowest of the borrow material hydraulic conductivity. We did a direct shear test, drained direct shear test under saturated conditions, under 3 different normal stresses, 25, 50, and 100 kPa. We developed this new apparatus, which allows 8 inches by 8 inches by 3-inch high specimens. Given the grain sizes of these different materials, we decided to use a larger direct shear apparatus. And here are the results. Here is a typical result on, I believe these are on clean glass. We set up the machine so that we add the normal stress over about 5 minutes. And we monitor how much was the normal displacement or how much was the settlement, which gives us an idea of the compressibility of this material. And then the shear stress versus shear displacement plot, we took the peak values and ultimate values. And we were able to create more Coulomb failure envelopes using those for either peak or ultimate shear stress values. And here are aggregated data here. The 3 solid lines of peak shear stress versus normal stress plot are for the 3 Scarborough materials. And the other 3 dashed lines are for the 3 recycling facilities PGA. And there is some variation. 2 of the PGAs gave slightly higher failure stresses, but overall the peak friction angle was always higher than 45 degrees in this case, which seems to be a high enough number for any design. If we look at ultimate numbers, the lowest was about 40 degrees as shown in this plot. So the figure on the plot on the left is same as what we saw on the earlier slide with sand borrows versus recycling facilities PGA. But one on the right, instead of sand borrow materials, now we have clean glass with paper, clean glass with plastic, and clean glass with ceramics, 5% and 20%. And again, all of those fell above 45 degrees more Coulomb internal friction angle. So again, showing that the geotechnical properties seem to be acceptable for even if you had 5% paper added to the glass. Compressibility, again, all the data from sand borrows, recycling facilities clustered together. We had a slightly higher settlement when we had 5% paper added. As one can imagine, 5% paper is a lot of paper. But considering it was that much paper, the results are fairly reasonable. So what we learned from this research question is that the geotechnical properties of PGAs are comparable to those of borrow soils, and we can, it seems like even up to 5% deleterious material content can be allowable. And we also were able to show that up to 20% of ceramic added did not have much impact on the geotechnical properties of PGA in an adverse way. So with that, I'm going to turn it over to Matt about the next research question. Matt, can you share this?
Yeah, I think let's play from the current slide. All right. So let's see if I can minimize this.
I will stop sharing and you can.
Yep, no, I think we're good.
Okay, good.
Yep. All right. So I want to briefly talk about the economic analyses and the initial environmental life cycle assessment that we considered, specifically related to greenhouse gas emissions. And so, again, we focused on case studies in Vermont, and I'll share results from looking at the 2 largest materials recovery facilities in Vermont. So just briefly, where recycled glass in Vermont goes. And so in the year we were looking at, 2022, there were 21,000 tons of glass that were recycled. This doesn't include any glass that ended up in the landfill. But of that, about 7,300 tons is part of the bottle bill glass. And so meaning this is glass that people take to drop-off centers to get their nickels back. And that's about 7,300 tons. But 13,600 tons is ultimately sent to materials recovery facilities. And so we looked at the two largest, so one that processes about 5,500 tons of PGA annually, and the other one processing about 5,000 tons. And so, as was mentioned earlier, this PGA that's produced has multiple outputs. And so 76% stays in Vermont, but then 23% is shipped to Massachusetts, and then small amounts are also shipped to Connecticut and Quebec. And that's for the first materials recovery facility. And for MRF2, the glass from this facility is shipped to South Carolina. And so we first wanted to look at the economics using, I'm just going to focus on MRF1. Oh, and sorry, just to mention, if you're wondering, this 13,600 tons per year of processed glass aggregate, V-Trans alone used 14,000 tons in the study year. And so conveniently, these numbers are quite close. But if we look at the economics, this facility, MRF1, processing 5,490 tons a year, the tipping income, so the amount that they charge that can be associated with the glass, is $520,000 a year. Of this, there's $455,000 in processing fees. And associated with the current end use of PGA and shipping it to multiple locations, it's something that they pay for, which is about $250,000 a year. And so currently we estimate they're losing about $33 per ton of PGA. And they're aware, and we know generally that PGA is a cost for these facilities. The one scenario we considered was actually just giving away the PGA, so processing it, keeping it on the site, letting contractors or suppliers come and pick it up. And so essentially what that means is the transportation fees would just go away. And if you do that, there's actually some income associated with the PGA of about $12 per ton. And so we also looked at facilities, imagining a facility that doesn't have any the infrastructure to actually produce PGA. And so we considered what it would look like if you had to purchase this equipment brand new. And so this equipment and the associated equipment works out to about $2.3 million for a facility this size. Operations and maintenance end up at about $16,000 per year. And so looking at this over the course of 20 years with a discount factor of 5%, the minimum selling price for glass would be $11 per ton. And so to give an idea, the average sandboro cost in Vermont in 2022 was about $17 per ton. And so raw material cost, it still should work out to be within the range of what we expect for sandboro. All right. To wrap up, we also looked at CO2 emissions. And so again, based on the current transport of PGA, transport is the greatest contributor to CO2 emissions. And if you look at MRF2, that's shipping the PGA even further away, there's significant emissions associated with this transport. And so in these scenarios, transport really drives the CO2 emissions. There's also some emissions associated with operating equipment, as well as running the crusher. So when we look at hauling the PGA to a current aggregate distributor, we'll call them, so a sand pit, we essentially reduce emissions by 76% for MRF1 and 83% for MRF2. And so there's significant CO2 savings when we think about local use of PGA rather than shipping it out of state. All right, so to wrap up the entire presentation, like Mandar was saying, Protocol 1 is simple and reliable for routine assessments to determine deleterious material content. There are some limitations in that it will not capture ferrous metals or ceramics, but non-ferrous metals are expected to be insignificant in terms of mass, and ceramics up to 20% did not affect geotechnical properties. Protocol 2, this density separation or float test, it's recommended only if plastic content wants to be determined. It gives a generally high estimate of plastic content, but if you want a more accurate count of plastics, an FTIR can be used, but it is onerous. Also, geotechnical properties of PGA are acceptable, and it seems that 5% deleterious material content can be allowable. And finally, using PGA's sandbar replacement reduces the cost of managing glass. It provides a potential revenue stream for MRFs, and the local use of PGA greatly reduces environmental impacts. So with that, I'd just like to thank you all for joining us today.
Thank you so much. That was really incredible. I want to invite people to keep popping questions into the Q&A feature if you would like. I'm working on sharing my screen right now. Doing that and talking, not my forte, but we're getting there. Awesome. And you're all seeing my screen with the April webinar?
Yes, there seems to be one question so far.
Yep.
So paper does burn completely, but there is some ash left in the right, Matt?
Yeah, that's correct. There's a small amount of ash that does remain from paper residues. It is quite small, but it's there.
Has anyone complained about the spread of microplastics as part of the deleterious material? I will let Nick answer it. That was part of our motivation to determine the deleterious material plastic content, which appears to be quite small in the materials we tested. If it is going to be contained as a drain material or something like that, it feels much better than if you were going to use it as a replacement sand for I saw someone recommend once to use PGA for seashores when you get erosion of sand, which probably is not a good idea because then that material, the plastic, will get into the water. But Nick, what is your perspective on this?
Yeah, I mean, you pretty well answered it, but from my perspective, there definitely was a concern that our partners at A&R raised as we sort of, worked our way through this project. And to Mandar's point, that's why there was that, I think partway through the project, we sort of added that goal of being able to analyze the plastics content. And I did want to just touch on that first question regarding burning of the paper. I mean, I just wanted to clarify, in the HMA process, I believe they're referring to, making asphalt. But to clarify, this project just focused on unbound applications for this material. Mandar, do you see next question regarding glass angularity?
Yes. I cannot say that I know the answer fully to the second part, if it could be controlled during the PGA making process. If I remember from the facility, I think every time they produce it, it looks very similar in terms of grain size distribution. I don't know if they can tweak certain parts to change the angularity or not. In terms of how to measure it, it's probably possible, but we haven't looked into it. I was
Right now,
going to
oh,
go
go
ahead.
ahead.
Oh,
I was
I
just
was
going to
just
say,
going
this here is a link to contact the TIDC. We can direct your questions if anyone has any others. But if not, we still have 10 minutes left, and so I'm happy to invite discussion.
I was going to add that Nick is helping us interact with AASHTO's M318 committee to see if we can get these protocols into their document. So hopefully these will be helpful for everyone nationwide. What we have observed so far, the question is, are there any safety concerns similar to silica? The glass, one would think, is abrasive on your hands if you were to handle it directly, and it is slightly, but not bad. In terms of dust, we haven't noticed a whole lot of issues with that. So my answer is that there are not significant safety concerns similar to silica.
There's a question in the chat about whether or not we'll be sharing presentation slides with the attendees. I think that can be up to individual researchers if you're wanting to share your slides or not.
Yeah, I would rather not put them on TIDC website, but if someone wanted to, we can certainly share them one-on-one. So if someone emails me, I'll be happy to send them a PDF version of the slides.
Okay, those are all of our questions for today. I still have the QR code up if anybody else is looking to contact the TIDC or anybody about further questions. I want to take this time to remind you all that the annual conference for the Transportation Infrastructure and Durability Center will be August 6th through 7th up here on campus at the University of Maine in Orono, Maine, just a little north of Bangor, Maine. If you haven't been to campus yet, it's a really lovely spot to have a conference. And every single year, the discussion presentations are so great, but also the community that is made, and a lot of great research is shared that turns into collaboration. So definitely get this on your calendars, and we will be sharing information about registration very soon. But with that, that is really all the time that we have. Please submit your questions if you have any more. We're happy to answer them. And thank you so much for joining us for the April webinar. We will be announcing our next webinar very soon.
Thank you, everyone. Thanks, Nick.
Thank you. Take care.
Take care.